This question is about the Apollo 15 mission that landed on the moon in 1971. It shows the astronaut David Scott dropping a hammer and a feather. They were released from rest, which means stationary, at the same time and from the same height. And both the hammer and the feather landed at the same time. The question goes on to show a graph of velocity against time for the hammer falling to the ground. Now we can see along the y-axis we've got velocity going up to a maximum of 2 meters per second, and we can see here we've got the x-axis showing the time. Now the time is not quite so straightforward because we've got to be able to work out the scale to see where exactly it hit the ground. Now if we look carefully we can see there are 10 boxes between 1.2 and 1.4. So this is 0.2. And if each box adds up to 0.2, then we can do 0.2 divided by 10 and we get that each box is 0.02 of a second. We've got 1, 2, 3 boxes after 1.2, so this value here is going to be equal to 1.26. We're asked to use the graph to calculate the acceleration due to gravity from the moon and give the unit. We can remember that a velocity time graph's gradient always gives the acceleration. So because we've already analysed the graph, this is going to be really easy. The change in y divided by the change in x is equal to the change in velocity over the change in time. The change in velocity was 2.0. The change in time was 1.26. And this gives us a value that rounds to 1.6. And the unit for acceleration is meters per second squared. The next question asks us to again use the graph, this time to calculate the height the hammer was dropped from. Now, the fact that it says height is what is going to confuse most students, because normally when we're talking about velocity time graphs, we might be able to use the graph to work out either the acceleration using the gradient, which we've just done, or we can work out the distance an object has travelled by working out the area. But of course, in this case, the height the hammer has fallen from is the distance travelled. So we're just going to work out the area of this triangle. Now, the area for a triangle, as I said, in this case is going to be equal to the distance or the height. The area of a triangle is half times the base times the height, which in this case is a half times the velocity times the time. So it's going to be equal to 2 times 1.26 divided by 2, that's from the half, and of course these two are going to cancel and we're going to get 1.26 meters. The next part of the question says that the gravitational field strength is smaller on the moon than on the Earth, and it asks us to suggest why. Well, this is because the moon is much less massive than the Earth, or it has a much lower density. You wouldn't get any marks for saying that the moon was smaller, because that doesn't take into account that the moon may be made out of a super dense elements like uranium, and then it may well have even a greater gravitational field strength than the Earth. So it's really important that we get across the idea that it's about the moon has less mass. The final part of the question asks us to think about what would happen if the same experiment, dropping a hammer and feather, was conducted on Earth. Now, of course, in this case, air resistance affects both the objects. It says that the feather will reach the ground after the hammer this time, even though the force of air resistance is smaller on the feather than on the hammer. It asks us to explain why the feather reaches the ground after the hammer. Now, let's imagine we've got our feather and we've got our hammer. The feather is going to have a very small amount of weight to start with, and the hammer is going to have a much larger force of weight. Now, as they start to fall, as well as the weight that remains the same for each one, we'll start to see drag starting to increase. Now, as you can see by looking at my diagram, for the feather, the drag is already the same as the feather's weight. So the forces are balanced, and therefore there's no more acceleration, and it's reached terminal velocity. And that terminal velocity is going to be very small. For the hammer, the drag hasn't balanced the weight, and so it's going to keep on accelerating, probably all the way until it hits the ground. So it's probably not going to fall far enough for it even to reach terminal velocity. So, the first thing to say for this question is that the feather has less mass, or you could say less weight in this case. So, it doesn't take long to reach terminal velocity, because the weight will be balanced by the drag quickly. So it falls at a lower average speed than the hammer.